start with what are the desirable attributes of protection, that in other words what do we want out of a protection system. So let's try to understand that. See, there are four characteristics that we need to worry about. One is dependability, another is security, third is selectivity, and fourth is reliability. I mean, they are not totally independent of each other, but they more or less summarize what are the important things that we aspire for in a protection system. So I would suggest, I would feel that, yeah, and then addition to that we have the issue that relaying should be fast and accurate, so speed as well as accuracy. Now let's look at the dependability. Now dependability, a relay is said to be dependable if it trips only when it is expected to trip. So it characterizes the correctness of its operation. That is the primary criteria that dependability captures. So in other words, it is a degree of certainty that the relay will operate correctly. And how do you improve the dependability of the relay? One way of improving is to make it more and more sensitive, so that it doesn't miss out on a fault. Even if it is having low magnitude fault currents, it should not miss it out. So dependability or percentage dependability is defined as the number of correct trippings divided by the total number of desired trips into 100. So you notice the distinction: correct tripping, desired trips. You see that clearly? So not all desired trips may happen. That is the important thing which you have to notice. You want some trip should have taken place, but the relay did not trip. That means this number need not be 100%. If number of correct trips is equal to number of desired trips, the dependability will be 100%. But some fault may go undetected, and therefore the dependability may be less than 100%. This may happen because, for example, a relay may underreach, or a distance relay may underreach or overreach. An overcurrent protection, you have set it for some fault current, but the earth resistance is higher or the ground fault is higher magnitude, so it didn't pick up, etc. So as I said, one way to improve dependability is to improve the sensitivity, which is the ability to pick up on the smallest possible fault. The next important attribute that we need to worry about is security. So security is the property used to characterize false tripping, the other way around. Dependability is used to characterize the correctness of tripping. Security is property which is used to characterize the incorrect operation of the relay. So a relay is said to be secure if it does not trip when it is not expected to trip. Is that clear? I mean, that is also very equally important. You won't want to eat a medicine when it is not expected of you, because you are wrongly diagnosed for something and given a wrong medicine. That's not what you want, right? So that's the kind of situation here. Incorrect operation is a wrong diagnosis followed by a wrong treatment, which is opening of a line or a circuit breaker. You don't want that to happen. So dependability is also very important. Correct diagnosis. Security is also very, very important, which is that you should not be diagnosed wrongly. So it is the security can be improved by improving the selectivity of the relay. I will come to what is the selectivity of the relay in the next slide. But percentage security therefore can be defined as number of correct trippings divided by total number of trippings into 100. So if the number of correct trippings, if all the correct trippings, there was no incorrect tripping, then this number would be 100. Number of correct trippings equal to total number of trippings, then the security would be 100. But that doesn't mean that the dependability is 100. That necessarily need not mean that the dependability is 100, because dependability is divided by number of desired trippings. There may have been some events which you may not have detected. So security being 100 does not mean that 100% does not mean that dependability is 100%. Similarly, dependability being 100% does not necessarily mean that security is 100%. That both of them, therefore both the objectives are required for characterization. Now selectivity. So selectivity is the ability to correctly locate and classify the fault. Is the ability to correctly locate and classify the fault. A relay should be able to discriminate whether the fault is in its jurisdiction or not. So what we are talking here is, what we are discussing here is that look at this relay 1. Now it is supposed to, this is a radial system, it is supposed to protect the feeder 1, while the relay R2 is supposed to protect the feeder 2. So we don't want relay R1 to pick up on fault F2, and we don't want relay, and we want relay R1 to pick up on fault F1. So in that sense the jurisdiction of line is up to this bus, and jurisdiction of this relay is up to this bus. Here I am expecting that there may be a separate bus fault detector here. If it is not, then the jurisdiction of relay is also bus as well as the corresponding line. So this jurisdiction is also called the zone of protection. Now you can see here that as far as this fault current, if this was a overcurrent relay or a distance relay, it won't see much difference in the fault current or impedance if the fault is at F1 or F2 just before or after the circuit breaker R2. So this brings out to you the important issue that it is not very easy to provide selectivity. On paper you may be able to you may draw a box and say this is the zone of this relay and that is the zone of this other relay and so on. But in practice, to provide that functionality is not very easy. There is a gray area there where you are not able to properly distinguish whether it is on this side or that side of the bus, and that is a issue which we need to address. So selectivity, but if our relay was very selective, then it would automatically tend to become more secure because it won't maloperate. When it maloperates, it's usually here in this region where the border region, the boundary region, this is where problem of security will come in. The fault is just beyond the boundary region and it will pick up. So it's a maloperation of the relay. So that the boundary region, if you could crisply demarcate, that means not on paper but the relay could crisply see its boundary of operation, then independent of the topology of the system, independent of the generating conditions, independent of the loading conditions and so on, then it would actually be very selective, and by being selective it would also tend to be more secure in its operation. Now selectivity is usually provided by one simple method of providing selectivity is time discrimination. So what do you do in time discrimination? Look at this figure, for example here. Suppose the fault is at F2, then R2 will also see it, R1 will also see it. R1 action is time delayed with respect to the R2 action. So what will happen if the R2 sees the fault, it will act prior to R1, thereby R2 clearing the fault and not R1 clearing the fault. So selectivity has been obtained at the cost of time. That is, we have obtained selectivity by doing a time discrimination. On the other hand, if the fault was at F1, then what would happen? The relay R2 will not see this fault because this is a radial system with single source. If it was a system with radial system with sources at both ends, then irrespective of fault being at F1 or F2, the R2 would have seen it. But in this particular slide which I have taken, the relay is this is a radial system with single source, so R1 will only see the fault F1, R2 will not see any fault current. I am assuming a bolted fault here, 3-phase bolted fault, and hence automatically R1 will operate and R2 will not operate. So we have provided selectivity by doing time discrimination. A better way of providing selectivity is to apply a differential protection principle. So in this particular case, for example, what we have done, connected a CT here, connected a CT here, set up a circulating current in absence of the fault. If there is a fault, then the differential current will flow through the element and this relay will pick up. If the fault is outside of this boundary, then the current here and the current here would be identical, and therefore circulating current would only be set up, and therefore the CT would not, the differential element will not pick up, and therefore there will not be any maloperation of it. So current differential protection very crisply defines the boundary of the protection. It is right here at the CT. This bus fault is no more detected by this particular scheme. The distance and the overcurrent protection do not provide a crisp boundary of protection. It's only differential protection where a very crisp demarcation of the boundary of protection is done, and that is physical boundary where you place the current transformer. So this scheme is actually not, the difference between distance and overcurrent protection is distance overcurrent as one class and current differential as another class, is that those protection schemes are based only on the local measurement, while this particular scheme is not based upon local measurement. You are getting information from the other end of the transmission line. It may be 10 kilometers, 20 kilometers short line, or it may be 200 kilometers with a fiber optic communication link passing the information. That is not the issue, but the point is this differential protection uses information at the other end of the line, and that is that additional communication is what makes it more secure in its operation. Reliability. So it's finally, what do we want? We want, at the end of the day, we want reliability. So reliability is the ability not to fail in its function. So it can be achieved by redundancy. So one of the ways of achieving reliability is redundancy. For example, any important transmission line, you will not have one single protection system protecting it. You will have multiple protection systems, maybe of different philosophies, protecting it, so that the fault on it does not go undetected. For example, if you have a 400 kV line, you would have typically a pilot wire protection on it, or a kind of current differential scheme, and distance may be the backup protection for it. So it is, and then you will do the ORing of the two logics to take a trip decision. You won't ORing or ANDing. There can be multiple ways of looking at it. They will look at that issue later on. But if your main concern is dependability, then you can have two independent protection systems, preferably with two different algorithms running onto it, not just identical systems duplicated, and then trying to protect it, then trying to provide that. So that is one way of doing it. The other way of providing reliability is to do a backup protection. So backup is at another terminal. So it's at a distant place. Another bus, a relay, like for example here, a relay R1 can be used to back up faults protection on this particular feeder segment. Why should you do that? Because if you do a backup here, local backup here with another duplicating another protection system, it still doesn't mean that you are 100% sure that you have provided a backup protection. For example, if they are sharing a common DC battery, for example, and the battery fails, so here we are talking not just of backup action, reliability. When we are talking of the relay, we are talking of circuit breaker, we are talking of the complete thing which finally opens up and clears this fault, for example. So one thing is that if this breaker is stuck, then you need to, for example, in this particular case, open this breaker. So that is one issue. Other issue is that you had two duplicating systems, suppose sharing some common wire or a common LAN cable, or or a common DC source which was powering them and the power failed there, then that common mode failure would affect both of them and therefore they will not operate. So when you have a local backup, you should otherwise make very sure that you don't have any common mode failures there. Otherwise, again, the reliability is not achieved. And the last point is the catastrophic failure. For example, an earthquake takes place at the substation, disrupting everything there. So if you had a redundant duplicating system there, it is of no use, or a CT burst happens, and a CT is not duplicated, a CT burst happens, then what do you do? So you don't have so the local duplicating it, making it redundant automatically does not solve the problem of backup protection. So still a remote backup, the remote backup is very important. This point has been confused a lot typically in the recent past, where quite a few relaying system, quite a few blackouts have been pinpointed on maloperation of distance relays or overcurrent relays, and therefore there has been this kind of for example talk that zone 3 of distance relay is not required, it is no more required and so on, because it picks up on low voltage conditions, etc., thereby creating some trippings which further worsen the voltage scenario and create a cascade effect. But the point is, people who argue against that kind of a backup protection, against such a zone 3 backup, for example, because of some problems which they foresee, because of the complications that they see in a developing voltage collapse scenario, maloperation of relay and so on, forget that if this zone 3 backup, for example, was not there, then there is no proper protection itself available. As I said, if there is a catastrophic failure or a CT burst or some such earthquake or whatever, it's only the remote backup which will work. It is not the local backup which will work. So a remote backup is a necessity. So unless one invents better ways of doing remote backup, it's not possible to replace or say that we will shut off zone 3 of a distance relay element, because remote backup is a necessity. You cannot just duplicate protection systems at the same place and get that kind of reliability in protection as a remote backup achieves. So remote backup is a must, even though zone 3 has its own disadvantages of picking up on low voltage conditions and so on. So that part is accepted, but throwing it out per se itself is not a solution to the problem. So we will so that is the reliability, and the measure of the reliability is number of correct trips divided by number of desired trips plus number of incorrect trips, that is the ratio. So here correct trips, desired trips, incorrect trips, so everything is factored. By desired trips we are factoring the dependability, by incorrect trips we are factoring the security. So this definition or this measure of reliability is 100% only if the number of correct trips is equal to number of desired trips, and therefore the number of incorrect trips are 0. If the number of correct trips is equal to number of desired trips, but there were some incorrect trips, even then the reliability will not be 100%. So that's why it's a combination. So all of us know about this zone of protection and so on. The point is, there are two important issues. One is that zones have to overlap. So you cannot have zones of protection. You cannot have in this whole transmission distribution system any part of the system which is left unprotected. So zones have to overlap. The second point which I mentioned earlier, I have mentioned that point earlier, that on paper you will draw very crisp zones, but actual relays may not give you those crisp demarcation boundaries. Distance relays and overcurrents particularly don't give you that kind of a crisp demarcation of as you show on the figure. So it's good to draw on the figure, this is the zone, that is the zone, but that kind of crispness is not seen unless you use current differential protection, where the CT physical boundaries actually define the zone of the protection. So it's a good concept, but the application of it is, the relays don't per se directly give you a very crisp boundary of protection. Okay, now let's look at the speed requirements of the relay. So there are two things: maximize safety, minimize equipment damage. The third thing is that the slowness of the protection system can worsen the system stability. So therefore speed becomes also important in a high voltage system. As your voltage level goes higher, the speed also becomes important, because a fault lasting there may create a instability due to significant acceleration of the rotors. So these are the three important issues that we need to worry about. Right now, what is the kind of speed which you get from a circuit breaker? What kind of speeds do we get from a circuit breaker? Yeah, 3 to 4 cycles. At the best 2 cycles, not better than that. So what would be the primary protection time, operating time for a relay? How much time should a relay pick up? 2 cycles, 1 cycle? 1 cycle. Oh, okay, less than 1 cycle. See, this depends upon many things. First of all, for example, if you have if your protection system is not very critical, then you can even put a fuse and get a much higher operating time and still live with it, right? So when you say 1 cycle, you are thinking of a EHV system or some such thing in the back of your mind, and therefore you want that high speed of protection. But actually 1 cycle may also be a very long time for protection, because of another problem, which is that your protection system gets inputs from what? CTs and VTs, the voltage transformers and the current transformers, and in 1 cycle the current transformer itself may saturate partially or completely, and therefore the speed also depends upon the application and the sensors that you are using. So for distance protection, maybe 1 cycle may be okay, 1 cycle may be okay, but for busbar protection, differential busbar protection with numerical relays, operating time of around quarter cycle is prescribed. So you need much faster relays than that, not because the critical clearing time of the time in the system is very small. That's not the reason. The reason is that your sensors performance may degrade significantly after the fault. In particular, due to the iron element, the CT core may saturate on decaying DC offset current, and therefore the differential protection system may maloperate, may not operate, and so on. So depends upon the application. Distance application, half to 1 cycle is okay. Current differential protection with numerical relays, you require around a quarter cycle of operating time is what is prescribed, because CT performance has to be very accurate while the relaying decision is being taken. Another interesting thing on this point I would like to mention is that it happens like the analog relays were faster than the distance relays, than the numerical relays when we look at things like distance protection. So it's not that if you go and put a microprocessor based relay, automatically it becomes fast, because there is an algorithm which is running into it. The algorithm needs certain time to calculate something in a digital way. Here what you are doing, you are estimating phasors using discrete Fourier transform at the very bottom level. That is what you are doing in a numerical relay. So if it takes one cycle or half cycle or whatever to accurately estimate a phasor, you have to wait, and post fault that much of data has to come into your processor before it makes an accurate estimation and then it picks up, and therefore there is some minimum delay which is there. But an analog instrument like a electromechanical relay or a solid state relay may not be actually doing that way, so it's continuously processing and may pick up faster. So the distance relaying speeds still tend to be a bit lower than the analog processing things, and that calls for innovations in the estimation of phasor. So DFT, full cycle algorithm, half cycle algorithm, then there are algorithms based upon phasor-lets which have been proposed by GE, essentially people working in GE, essentially to address this kind of issues. And that brings us to the speed versus accuracy conflict. You cannot improve accuracy beyond a certain extent without, while still improving the speed. As you try to make your algorithm faster, there is a limit after which you will start automatically, speed will imply that your accuracy is being sacrificed, and there is that trade-off which you will have to undertake. So we will look into different algorithms of phasor estimation, how they can be made faster, and we will look at the frequency response of those algorithms to show that the faster algorithms don't have that good frequency response, which is the trade-off which we are getting on the accuracy. So we will show through proper analysis. We will see how we improve speed, and at the same time we tend to sacrifice on the accuracy, but then how we also work out the trade-off. It's the third thing is, therefore when there is this thing happening, we need to have a measure in our mind as to what is the trade-off. So where the loss of accuracy is acceptable, where the loss of accuracy is not acceptable, which segment we are of the frequency spectrum are we concentrating on, and so on. So those kind of trade-offs we will also see later on. Okay, now to come to the stability aspect, there is a simple example which all of you must be already aware of. This is a single machine infinite bus double two transmission lines. There is a fault F1 here close to the machine. After the fault, earlier the trajectory P delta characteristic was this one. When the fault is there, system moves from operating point A to F, and then because of the PM minus PE unbalance, the rotor starts accelerating, so d omega by dt is positive, so the angle starts increasing. At this point here, the fault is cleared, this particular line trips, and therefore with only one line in service, the P delta characteristic is given by this particular trajectory, and once the fault is cleared, the angle or you jump on to this particular the P jumps onto this particular trajectory. So therefore the trajectory now comes onto this violet kind of segment, and now PE is greater than PM, so the machine starts deaccelerating. So PE is greater than PM, so there is a deacceleration, but still the speed is larger, and therefore the rotor tends to accelerate until this point here where the speeds become equal, the d delta by dt goes to 0, and you hit the delta max point. Beyond this, what happens? The deacceleration starts because PE is still greater than PM, and now the omega goes below the normal speed, and the machine angle keeps on retarding until it crosses this particular point, where after the machine starts, the acceleration starts on this. But even though the acceleration starts, the speed is still much below the synchronous speed, and therefore the deacceleration of the rotor continues in delta until you hit this limiting point somewhere here, where the speed becomes equal to the synchronous speed, and now still accelerating power is available. So therefore the rotor starts accelerating and the machine angle starts picking up. In absence of any damping, this phenomena would have continued till an infinite period of time, but because there are so many electrical and mechanical damping issues, systems which are working in the place, so therefore over a period of time the oscillations will die down and settle at this new equilibrium point O. And this is the area which, from the equal area criteria, this is the acceleration area, this is the deceleration area, and for a stable system acceleration area has to be equal to the deceleration area. So therefore this is the stability margin which is available to you, and once if this peak delta max point E, if for some reason it crossed this particular point G, then there is no way the generator or the rotor will come back, because now from point G onwards the deceleration is no more available, the machine again starts accelerating because PM is greater than PE, and you have hit into out of step condition. So when that happens, we say that the machine has gone out of step with respect to the bus, or the two machine system has gone out of step. So the largest fault clearing time that can be allowed without creating a out of step or a unstable situation is called the critical clearing time, and the circuit breaker operating times will be typically much lower than the critical clearing time. I mean, nobody designs a power system in which the protection operating times, protection system operating time inclusive of circuit breaker operating time is close to critical clearing time. But in a system where abnormal things are taking place, like lines are getting tripped, cascade trippings are taking place, this critical clearing time may start reducing. So you need to worry about that also. Okay, now we have already discussed speed and accuracy about this, except that I like to talk, when I talk of speed and accuracy conflict, I usually like to talk of one that simple example of driving fast on the road. You know, if you drive very fast on the road, more likely that you will make accidents, because essentially you tend to become rash. So speed versus accuracy is conflict is something which we are actually very we have seen it very closely, but we also know that there are ways of improving it by improving road conditions, make road broader, make your equipment better, and so on. So there is certain way in which you can beat it, but up to a certain extent. I mean, you can keep on pushing the limits, but there are always limits which are still there, and the question is how do you push them. Okay, so that covers this particular lecture. Okay, so now we will start with a quick review of sequence components. So it's very important for a protection system engineer to have a good understanding of sequence currents and how machine reacts to different sequence currents and so on. So it's pretty important to do this. By the way, all this material which I am putting here is already available on my web course, and there are some, for example, in sequence currents, components and so on, there are some good animations or illustrations which I don't have here on PDF, so you can actually go there and check up how graphical illustrations and so on. You can directly go to the web course and click there and see, but I don't have them here on the PDF. So now in this we will look at sequence currents as well as short circuit analysis. So two things which I want to now review: the sequence currents and short circuit analysis. Okay, so these are some standard things. Sources of fault current, will more or less quickly go through it. I mean, you can read it there, and I don't want to elaborate on it. Sequence components, or this concept was proposed by Charles Fortescue way back in 1918. So like we have 50 years of IIT, if somebody celebrates, then silver, gold, platinum, all jubilees are over, but the concept is still very much there, used by practicing engineers as well as theory people as much as it was used. So what is it that makes it special, or what was that brilliant idea that he had which made it special? So look, what we are what he was analyzing was working of an unbalanced system. Now, in fact, if you look at his original paper, he is talked of n-phase system. He is not talked of three-phase system the way we now read it in books, because probably at that point of time people were debating whether it should be three-phase system or six-phase system or multi-phase, how many phases and so on. So his concept was on n-phase system. So, and what you are studying is an unbalanced system. So if you take three-phase system, unbalanced system, then you have how many unknowns? 6 unknowns, because every phasor, to put it on a paper, you need to know its magnitude and you want to know its angle. So therefore there are 6 degrees of unknowns or 6 unknowns in a three-phase system. But if you look at a balanced system, then how many unknowns are there? Only 2, the length and where you place it on your paper, so angle. So what he conceived, and that was the brilliant part of it, that why can't an unbalanced system which is having 6 degrees of freedom be thought of as made up of 3 balanced systems each having 2 degrees of freedom. If that thought comes to you, then the rest of it can come to you through provided your education is up to mark, you know your maths and so on and so forth, then the rest of it is in the machinery. What I mean to say is, this was the idea, the remaining part is the machinery which you have to develop around that particular idea. So 6 degrees of freedom in an unbalanced system can be thought of as made up of 3 balanced systems each having 2 degrees of freedom. So each of those balanced system, in this particular case we called it as the positive sequence component, the negative sequence component and the zero sequence component. So positive sequence component, VB lags I call it as ABC phasors. So the B phase lags A phase by 120 degrees, the C phase lags B phase by 120 degrees, the magnitude is identical. And to describe this, we use an operator A which is e to the power j 2 pi by 3, and therefore B phase lags by 120 degrees, so it is A inverse which is A square, so therefore leads by 240 degrees, and C phase leads by 120 degrees. The positive sequence quantities. So this is the anti-clockwise direction is how you rotate the circle, right? I mean, that's the way it is. Now the negative sequence component, the B phase leads by 120 degree and the C phase lags by 120 degree. So this is a negative sequence phasor, and the zero sequence phasor. The zero sequence phasor is the special thing, the tricky thing. It meets the technical requirements, all magnitudes are equal and all are equally placed with respect to each other. In this particular case, the angle is 0 among all of them. So still technically it is equidistant, and at the same time particularly the angle is 0. So whether you have 5-phase system or 7-phase system or 6-phase system, the zero sequence will always be there. The positive sequence will always be there, but there would be many more in between systems, which in 3-phase case we have only positive, negative and 0. This B is this is a mistake, the 0 phase sequence. The application of 0 sequence voltage will not cause any rotation of an induction motor. The reason is the MMF which is created in the air gap would be 0. To create a rotating EMF, what do you need? You need a sinusoidal distributed MMF, and you need a spatial, I mean the current should be, excitation should be sinusoid distributed, and the spatial distribution of MMF should also be distributed. The product of it gives you that 3 by 2f sine of omega t minus theta kind of a equation, which is the equation of rotating MMF. So distributed winding and in time distributed current creates a rotating MMF. So if you just give the same current excitation to the 3 windings, the net MMF which will be created in the air gap by symmetry would be 0, because the winding is distributed, the currents are identical, so in the air gap the MMF created would be 0, therefore there will not be any rotating this thing. Okay. So these are animated pictures in the web course, you can look at it. Mathematical description of this. I guess all of you are aware of this mathematical description, right? The point to note here is that this is exactly what is a linear transformation. So in the terms of linear algebra or modern algebra or whatever, a sequence transformation is nothing but a linear transformation, because this matrix is made up of constant elements. And why do I call it transformation? Because the matrix here, the transformation matrix T here, is a invertible matrix. So that is why I call it a transformation. If this matrix T was not invertible, then when you went from 0, 1, 2 domain to ABC domain, you would have lost information, which would, and therefore when you could not have come back to this particular place again. When you say a transformation, you change domain without loss of information, and then you can come back to the original domain without any loss, because there was no loss of information. So this matrix being invertible guarantees that there is no loss of information. That's what constitutes a transformation or a invertible transformation, or whatever you want to call it. Further, the inverse of this matrix is also much more simple. The inverse is also much more simple, in the sense that the reason being that the columns and the rows in this matrix T are orthogonal to each other. So what does that mean? If some x is one column, xi is one column, xj is another column, xi transpose complex conjugate times xj is equal to 0. So the Hermitian operator you have to apply. It's not just in real matrices, you only do transpose. So x transpose y is equal to 0 is what we say if the x and y are orthogonal vectors, if x and y are real vectors. But with complex vectors, it is x h superscript h x h y to be equal to 0, and that h operator means the x is first transposed, and then every element you have done a complex conjugate of it. So by that way you can check that all these rows and columns here are orthogonal to each other, but the length of each of the columns is not unity. The length is under root of 3, and therefore in a sense, like what we call power invariant transformations and so on, this is not a power invariant transformation, because it's not an orthonormal matrix. It's not an orthonormal matrix, even though it's an orthogonal matrix. Okay, so what this allows you, this transformation allows you, that when it is convenient, you represent things in sequence domain and work. When it is convenient, you represent things in phase domain and work. So both of them are identical. That's what essentially the transformation says. Choose what is convenient and work in that particular domain. Now, as far as computations like short circuit analysis and so on are concerned, there is no major advantage with today's computers to do anything in sequence domain. You can do it directly in phase coordinates. You can do short circuit analysis in 3 phase coordinates, probably in a much better generic way than what you do in a sequence domain. Because when we do sequence domain, as you will see soon, we also want to exploit the advantages. We want to have some symmetries and so on and so forth, which is not required if you directly work in phase domain. So from a computational standpoint of view, probably there is not now much advantage with the computing power which is available to you. There is not much advantage to work in sequence components, but still the physical description, like a ground fault is a zero sequence current, or a negative sequence current causes a MMF to rotate in the opposite direction. These concepts are all very valid, and these descriptions are all very useful to engineer. So what I am trying to say is that sequence as an application, just giving unbalanced data to you does not make sense. You know, you to infer something out of it, you have to do some more processing on that data, and then only your inferences will come out. Just I present you unbalanced data, it is not going to help you. So that inference engine, sequence components as an inference engine for unbalanced systems is very, very valid even today. But to do computations, one can directly do it in phase coordinates. So one need not think that those diagrams that you have studied, you know, like SLG fault, positive sequence in series with negative sequence in series with zero sequence, and all that, without that I cannot calculate fault current and so on. It's not like that. I can model the system in three-phase domain, I can directly put a ground fault, I can directly calculate the fault current, I mean without any recourse to remembering those complicated diagrams. And in fact I can take very typical faults, I can directly have simultaneous faults, I can have something open circuited at the same time something short circuited, and all that I can do with ease in phase coordinates, and without any necessity to know all these kinds of connection diagrams. So computation point of view, directly three-phase coordinates seems good now, but inference of all of it has to still to be done in the sequence domain. I mean that is where that is where I see the key utility of it. So we have seen this. Okay, let's look at modeling of the network in sequence domain. So sequence component analysis is used when the network is balanced but the phasors or loads are unbalanced. So you convert ABC to T matrix times I0, I1, AT, convert delta VA, delta VB, delta VC as T times delta V0, delta VA, delta VC. This is a transmission line model in phase domain, symmetric and all that, transposed and so on. Take this T inverse here, then do this T inverse ZT. I mean you should do all that yourself because this is a review lecture, and then calculate the model in sequence domain. So what do you get? You get ZS. ZS is the self impedance, ZS is the mutual impedance between the conductors. So ZS plus 2Zm is the zero sequence impedance, ZS minus Zm is positive sequence impedance, and ZS minus Zm is negative sequence impedance. So what do you see? You see two things. One, if the transposition was there on the network, then the sequence components are decoupled with each other, right? So each of the sequence components can be analyzed independently. If however there was unbalance in this, then you would have got non-zero elements here, which would imply that sequence components are not decoupled with each other. Then there is no advantage of doing sequence components. But since transposition of lines, generators being symmetrical and so on, transformers being symmetrical and so on, are all very valid assumptions or realizations. So therefore most of the time this coupling between the different sequences would be absent, and therefore you can work with it. In normal case you are working only with positive sequence phasors. Do you see that clearly? This is zero sequence excitation is not there, negative sequence excitation is not there, so you are working with positive sequence phasors. So when you do a load flow, when you look at a load flow, the data and so on, the impedance is so and so, transmission line impedance is so and so. It is not per phase impedance. Many people carry this impression that it is some per phase impedance and so on. It's not that. It's a positive sequence impedance. It's a positive sequence impedance that you are using. What you are getting there is a ZS minus Zm. That is the data which you are getting. So positive sequence, all your actual steady state analysis that you do what you have done in a computer analysis course, for example, power systems course, is all based upon positive sequence data, not per phase data. And usually here in modeling sequence, you take a phase as the reference phasor. If you change the reference phasor, the matrix structure will change. You should try it yourself. It is all based upon the standard matrices which we show you are all based upon a phase as the reference phasor. Take B phase as a reference phasor, rewrite the sequence transformation matrix T and check that it is different from what we have shown here. But for convenience, it is always assumed that A phase is the reference phasor. Okay. So we have okay, this is the standard formulas which you use for three-phase fault currents. I think these formulas I won't go much into. You are all aware of. So here it shows lecture 10 and then I go to lecture 12, means actually on the web course lecture 11 was a tutorial this thing. So there are some solved problems and problems to be solved for which you can do yourself as a part of your own review exercise. So we will see modeling of static apparatus, synchronous machines and transformers. I mean, these are the three things which we want to look into, and then see what is the issue of short circuit analysis. Now advantages of per unit systems, I will skip this. I mean, all of you are aware of advantages of per unit system and so on. So you can just probably read the transparency once and we go forward. Okay, modeling of transmission lines. Now this model I have already told, we now just finished the modeling of transmission line in sequence domain, we just finished. The one point which you should note is that positive sequence impedance is equal to negative sequence impedance equal to Zs minus Zm, and the zero sequence impedance is different. That happens because of the symmetry and non-rotating region, non-rotating being a non-rotating device. So with a rotating device you won't get positive sequence is equal to negative sequence even if there is a symmetry, because the rotor cannot run simultaneously on clockwise and anti-clockwise direction. So the moment rotor direction changes, something changes in the system even if the static part is symmetric. So positive and negative sequence impedances are identical for transmission systems and for transmission lines and power transformers. They are same, but the zero sequence is different. And in computing zero sequence, we actually need to worry about the ground return. Where does the positive sequence and the negative sequence current go? Does it actually require the ground? It doesn't require the ground, because IA plus IB plus IC is always identically equal to 0. So basically, even if there is a ground, whatever resistance the ground may have, the drop which is taking place in it is 0. So for positive sequence and negative sequence, the earth potential or the ground potential, we consider it as 0 throughout, is a correct representation. But the ground for a current, actually in a zero sequence, the whole of the current has to go through the ground wire or the ground or the neutral wire or whatever. So what it means is, and the ground does not really have a infinite, it does not have a zero resistance per se. It's not really true. It depends upon the terrain, so on, so forth. If there is a neutral conductor, how you have grounded, so on and so forth. So it depends upon grounding practice and so on. So the point therefore is that you cannot consider ground to be a equipotential surface when you are talking of zero sequence component. So but we want to consider it as a equipotential zero potential surface only. So what we do is, we actually, whatever is the drop which is going to take place in that ground return, we add it into this value here, Zs plus 2Zm. Here we actually add that all that drop in the ground in this particular value, in this Zs plus 2Zm, and then calculate the Z0. So therefore, the calculation of Z0 is always based upon certain assumptions about what you consider your ground is. And therefore, actually estimate of Z0 may be far different from the design calculations of Z0, may be far different from maybe 5 to 10% different, up to 10% different from the actual values which may be there on the field, because you have made some assumptions on the return and used it here. But positive sequence and negative sequence calculations, impedance value calculations can be very accurate up to 2 to 3%. If your design data is accurate, then your actual calculations will also be very accurate. But zero sequence values are under certain assumptions which may not be true in that ground, so therefore a measurement will give you a more precise value of the zero sequence transmission line data. Another interesting thing which you need to look into is the mutual coupling. Whenever you do this short circuit analysis, a tower on which two circuits are going, you will find in the data that people specify zero sequence coupling between the two circuits, but there is no coupling specified on the positive and the negative sequence. That means the coupling in positive and negative sequence is zero, the coupling is only present on the zero sequence. So the reason for that, let's look at for the reason for that. Suppose that I only energize the circuit 1 A, B, C with positive sequence currents. Okay, now let's try to see what is the flux linking this particular, take a flux path which links the conductor A2 also. For example, this dotted path definitely links the conductor A2, because it also circles this flux path also circles the conductor A2, so therefore it links the conductor A2. And then if this flux is non-zero, this linkage is non-zero, then the rate of change of it will induce the voltage in the conductor E2, and therefore the mutual coupling phenomena would be seen. Now if your excitation is positive sequence, then now you know from Ampere's law that this total MMF across this H into L product throughout this circle is nothing but the net current which is inside of it, which is IA plus IB plus IC. So if the sequence current is a positive sequence current is given to ABC, then the net current is 0. So which means that no net flux actually links A2, and therefore the mutual coupling between the two positive sequence mutual coupling between circuit 1 and circuit 2 is 0. Same reasoning applies for the negative sequence also. But for zero sequence, what do you see? For zero sequence, you see that if these three currents are identical zero sequence I0, 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 then the total MMF linking this particular path is 3I0, which is non-zero, which means that the zero sequence, there is always a coupling. If two three-phase circuits are going close by to each other, then there will be zero sequence coupling between them, but the coupling will not be there in the positive or negative sequence. That is another reason why you need to worry about this in a short circuit analysis, but you will never worry about it in the positive sequence analysis. For example, what you do in load flow analysis. So in load flow analysis, people will give you one circuit, two circuit, three. They will never say coupling between them because it's negligible. But and that's probably one of the reasons why you can go and stay close to a transmission line without worrying about the magnetic fields also, because provided that it is nearly balanced, the magnetic field outside of it is not going to be very significant. You can go and live there. I mean, as there is no much magnetic field there, provided it's balanced. So is this point clear? So load flow, we don't worry about this, but short circuit analysis, we need to know how close the towers are. If they are close by, two circuits are on the same tower, then we need to worry about the mutual coupling in the zero sequence, but not in others. Yes. Positive, not positive. Positive, negative sequence, the circuits can be considered decoupled. Only the zero sequence voltages will come. This current here would give a zero sequence voltage on the other transmission line. You can show the same thing mathematically also. So this is the circuit 1 voltage drop across it due to its own currents, and if I have transposed it adequately, then I can assume that all mutual impedances between circuit 1 and circuit 2 are equal to alpha. Conductor A to conductor A, conductor A to conductor B of the other circuit, conductor A of first circuit and conductor C of the second circuit, all such are equal to alpha. So this matrix is J alpha into 1, 1, 1. Now this is in phase domain. Now the moment I transform this into sequence domain by doing a T inverse AT type of a transformation, you would see that I get Zs minus 2Zm, Zs minus Zm, Zs minus Zm, the standard ones, plus 3 alpha here. This is cut here, it's not fully come here, you check in the web course, and first term is only 3 alpha and all other terms are 0, 0. So the coupling is only coming with IA0, not with IA1 and IA2. So you can show the same thing using sequence transformations also. Okay, now let's look at the transformer. Again, the transformer is a static device. Positive and negative sequence impedances are identical. There is nothing to worry about positive and negative sequence admittances. But when we look at the zero sequence admittance, it will not be same as usually the positive sequence admittance. And it depends upon the construction of the transformer also, whether it's a core type transformer, whether it's a shell type transformer, and so on. If it's a core type transformer, you look at this particular picture here. Now phi A plus phi B plus phi C will always be equal to 0, right? I mean, you can draw the magnetic circuit and write that phi A plus phi B plus phi C is equal to 0. So if you provide zero sequence currents to the 3 windings, then it means that the zero sequence flux is actually going to be 0, which means that flux divided by current N phi by I is nothing but the inductance is actually the net inductance would also be 0. So the core type transformer should have theoretically a zero sequence inductance should be actually 0. But this actually the flux will not be 0. What it means is that the flux will leak out in the air path and the tanks and so on, creating some kind of heating there, provided that the tank don't saturate. So it will not have exactly 0 value, it will have some value but much smaller than the positive or the negative sequence impedance. So transmission line zero sequence impedance is 3 to 5 times, core type transformer the zero sequence impedance is much lower than the positive or the negative sequence impedance. Shell type transformer, if you look at the shell type transformer, what happens here? If you give zero sequence excitation to, if you give positive sequence excitation, these two limbs look redundant. Phi A, I mean A plus B plus C is equal to 0. I mean the 3 fluxes symmetrically add and go to 0. So these limbs, the 2 shell limbs are actually carrying the zero sequence flux. But when you give zero sequence currents here, then this flux will equally distribute through the outer 2 limbs and close the circuit. Now since they have an iron path, the reluctance is low and therefore N square by R or N1 N2 by R, from which you can infer that the inductance is going to be high because of the iron path which is available for flux to flow. In other words, the flux is appreciable. So the zero sequence flux is appreciable, therefore the zero sequence inductance is also appreciable. So for shell transformers, the zero sequence impedance is high. For core transformers, the zero sequence impedance is low. That's the conclusion. And if you have a bank of 3 single phase transformers, then the zero sequence impedance, positive, negative and zero sequence impedance are all identical. Okay, if you connect these in windings in delta, then the zero sequence current will not flow through in the line, right? Because you can see it here. This is the voltage, the drop, it just circulates here. I mean, I think all of us know that, so we don't need to get into it more. So I0 minus I0 is what flows here, which is equal to 0. These transformer connections, again the positive negative sequence are identical, and this is the zero sequence. This is the zero sequence diagram. For example, here what do you see? A circulating current can flow in this particular winding. So if the zero sequence current is circulating in this winding, it won't be seen in the line, so therefore you have kept it open here. But a circulating current here means there is corresponding zero sequence current in these windings also by the transformer action, and therefore look from this point, there is this total leakage inductance of the transformer gets a path to the ground. So therefore the total leakage impedance of the transformer gets a path to the ground here, but is seen as open from here. There is a ground impedance, then the 3 times ground impedance has to be added. If the two windings are delta, then what this shows is that there can be a circulating current, but it will not be seen at the lines at all. So therefore from both the lines it looks open. If it's grounded at both the sides, then it's just like any positive or negative sequence impedance. There is a connection between Z to L. The currents will flow through the line and therefore through this total leakage inductance. Even if one winding is, like if you have a star grounded and star ungrounded system, then no zero sequence current can flow here, because IA plus IB plus IC is equal to current in the neutral, which is 0, so I0 has to be 0. Then by the transformer action, no current can flow in the windings, primary windings also. So therefore it gets open from both the ends. Even though this provided a path for it to flow, none can flow. Same issue here. I mean, here is here open from here because it's delta and not grounded, therefore open from here. It's the leakage zero sequence impedance, correct. It is the zero sequence impedance here. Positive sequence here and zero sequence impedance here. It's shown as same ZC, so it's assumed like it's a bank of 3 single phase transformers. I mean, but otherwise zero sequence circuit has to be worked with the zero sequence impedance data only, not with the positive or negative sequence. And that's why actually this neutral is also shown different, N1, N2 and N0. Everybody is shown a different neutral, because just to emphasize that the ground issue is involved here but is not involved here. Okay, synchronous machines, positive sequence reactance would be either of XD double dash, XD dash or XD. I mean, the rough case, one of these three data will be used as the, depending upon where that fault strikes. If it's if immediately after the fault it is XD double dash, after some time XD dash, subsequently steady state it goes to XD. The synchronous condensers and motors also positive sequence data is in that sense similar. Now if you look at the negative sequence data, then what happens when the negative sequence flux is there in the stator, then the rotor is rotating in is not latched on with that rotating flux. The negative sequence flux is rotating in opposite direction, the rotor is going in another direction, so there is a double frequency rotation which is actually seen by the rotor, not at all a static, relatively static condition, which means that the induced EMFs will come in the rotor and they will create currents to oppose that particular flux or the rate of change of flux as per the Lenz's law, which means that the net flux will tend to reduce. So the net flux tends to reduce means the inductance seen, effective inductance seen also reduces. So therefore the negative sequence impedance of is usually taken around 70 to 95% of the subtransient reactance. I mean, it will be lesser than the subtransient reactance, low. And zero sequence, as I said, symmetrical machine, ideally if you give zero sequence excitation to the primary, the flux in the core is zero, so therefore ideally the zero sequence inductance of the machine should be zero, but because there are this fractional pitching of the windings and so on and so forth, so non-idealities, so therefore the zero sequence impedance may vary from that value, being up from 0.1 to large range is possible. Yes, it will cylindrical, so that will also cause that variation. So long range is given here actually 0.1 to 0.7. Was it a question or was it a information? And if it was information, I would have accepted it. If it was a question, then I need to think on it. But I presume that cylindrical rotor machines may have lesser zero sequence this thing, because the iron is uniformly available through and through. But here the iron is not uniformly available. So the rotor is seen as, when you give zero sequence currents, the rotor is seen as a much more symmetric circuit if you have a cylindrical rotor. But the unsymmetric circuit is more seen with this thing, but you need to check it up. I mean, induction motors machines I will not get much into, because this course really does not go into much of fault currents with motors and so on and so forth. But the point is that it is effectively what you can take it as a subtransient reactance to begin with immediately after the fault for induction machine, and subsequently you can just put it by its nameplate impedance value or whatever, kV square by MVA as in a short circuit analysis. Electrical utility systems, you would take it as constant impedance. I mean, if the fault and the utility is far away, in that sense you are a fault on a distribution side and then the transmission sides and all that, generators will only see a notch addition in the current up, so therefore you outside effectively utility system can be modeled by a constant impedance for positive, negative and zero sequence. Loads, you can make it as an equivalent impedance and connect it to the diagonal of the positive sequence, this thing. Series transmission lines having series capacitor have a issue, because the series capacitors are connected in parallel with a protective device which is metal oxide varistors, and these metal oxide varistors actually, I mean, when the high fault current flows through this capacitor, then a over voltage develops across it. Because of that over voltage, this MOV will conduct. It's a varistor, it's a ZNO varistor. So as the voltage across it increases, it's a nonlinear resistor, so its resistance drops down. Now let us look at the this is the Y bus matrix in 3-phase domain. Each of these entries here is a 3x3 matrix. This Y bus is created using the normal rules of the admittance matrix formulation, except that everything here is a 3x3 entry. Now you apply sequence transformation on ABC here, and then rearrange the equations appropriately, that is couple the zero sequence, positive sequence by segregating, coupling these, I mean moving these variables also correctly here and there. Then what do you see? I0 is equal to Y bus 0 into V0, I bus 1 is equal to Y bus 1 into V bus 1, I bus 2 is equal to Y bus 2 into Y bus. So you get 3 sequence different matrices. So that's the decoupling which you are seeing. Now how do you really invert it? I mean, this is just these matrices, do you really invert it to calculate the Z bus and from there infer the Thevenin's equivalent? You really don't do that, right? I mean, you must have studied short circuit analysis in the computer aided power system analysis course, right? I mean, I am just going a bit fast on it, but you must have studied it somewhere, either in the CAPSA course or in your BTech course or something, right? Am I right or am I wrong? Yeah. So what we do here is to calculate the Z bus, from where we get the Thevenin's impedance and from that we calculate the fault current. What we do is, suppose I want the Thevenin's impedance at bus I. So what I will do is, zero sequence value suppose. Then I will take this equation, matrix equation, I bus 0 is equal to Y bus 0 into V bus 0, and put a current, I will inject a current of 1 ampere or 1 per unit, because this may be all in per unit. So 1 per unit at the bus I and 0 current everywhere else. 1 per unit at bus I, 0 current everywhere else. So what is it? I bus 0 then would correspond to ith column of the identity matrix. It will correspond to the ith column of identity matrix, and then I will solve this system of equation Y bus 0 into V bus is equal to Y bus 0 into V0 is equal to E1. So what I will do? I will do a forward back, I will do a LU decomposition of sparse LU decomposition of Y bus 0, and then from that sparse LU decomposition of Y bus 0, I will solve this and calculate the vector V, which is the corresponding ith column of the Z bus, and therefore its diagonal element will give me ZII and the other coupling with this. So to do it, I am not going to do an inversion. An inversion is actually n times more effort or much more than n times the effort. It's like calculating n such linear system of equations. So I will do a sparse factorization, LU factorization followed by a forward backward substitution. And similarly I will do for the positive sequence Thevenin's impedance and the negative sequence Thevenin's impedance also. Once that is done, once the corresponding Thevenin's impedances are obtained, then the fault current can be calculated using that standard table, like if it is a SLG fault, then put positive sequence, negative sequence, zero sequence in series and so on. So those standard things will be used. Finally, three-phase short circuit MVA, that is how you usually talk of breaker ratings and so on. So that would be three-phase current in per unit into three-phase MVA. If it is a SLG fault, the SLG curve, whatever is the fault current in per unit, multiply it by the three-phase MVA base, and that will give you the corresponding MVA of the three-phase or the fault short circuit MVA of this thing. Now we are almost at the end of this class also looks like.